So let's think about, where does this name ordinary least squares come from, right? When we're thinking about least squares, what are we trying to minimize essentially, right? Think about this graph, for example, in the bottom right corner. So we have X and we have Y and we have data on it. So we have a scatter plot, and essentially what we're trying to do is fit a line that goes through these points. And the way we pick the line, or the way the statistical software is going to pick the line, is by, it's going to look at different lines. So I'm going to draw lines of different colors here, this line or that line, and it's basically going to have all of these, figure out which rotation fits the data the best. And when we say the best, we basically mean the distance between the point, these different points, and the regression line, right? That distance, the square of that distance is the sum of the square of that distance is minimized. Okay, so that distance is what we call residuals, right? Residuals are basically the gap between the actual value of y, right? So we know what these points are. These are actual values. And we measure the distance between the actual values and the predicted value of y, right? So the predicted value is denoted by yi hat, right? And this is going to be somewhere on that line, right? So for each value of x, we can predict y. Okay, so here we can see that what we're trying to do is minimize the sum of squared residuals. Okay, now when we think about the OLS regression line, we're essentially thinking about this predicted value of y, right, given different values of x. So we've estimated, what we've done is through OLS, we've basically estimated beta naught hat and beta 1 hat. These are our OLS estimates. And for different values of x, we can predict what y is. Okay, so we come up with this regression line that we saw earlier. Okay, so we predict y for any sensible value of x. So sensible, we'll see what sensible values mean here, but this right here is called the sample regression function. So remember, without the hats, it was the population regression function that we talked about earlier. Now, the interpretation of beta naught hat is basically the value of y when x is 0, right? It's pretty much the y-intercept, okay? But you're going to encounter situations where this type of a prediction is pretty useless when we never find that x is equal to 0 in our data, right? So if x never turns 0 in our data, then that type of interpretation is pretty useless for us. In general, again, remember that we're capturing the slope here, which is basically giving us the changes in x, right? And we are basically predicting the changes in y. So remember what beta 1 hat is capturing, okay? So it's predicting the change in y for any reasonable changes in x. Okay, so in other words, if we wanted to simplify this further, we can say that if x changes by 1 unit, then the change in the predicted value of y is equal to the slope coefficient beta 1 hat. So let's put this to an example. Okay, so we're running with that same example of education, the effect of education on wages, and I took some data and I basically estimated the relationship. Okay, so here education refers to the highest grade that was completed, and wage is reported in dollars. Okay, so we've predicted this, and the sample regression function is given here with an intercept that was estimated and the slope coefficient that was estimated. Okay, and here our sample size was 759 observations. Okay, so the important thing here is to really discuss what do these estimates mean. Okay, so we want to focus on really interpreting this sample regression function. Okay, so first we look at what do we mean by this intercept, which we're finding to be negative 5.12. So we notice here that the intercept, like we said earlier, is basically when education is equal to 0, right? So if we plug in education equals 0, then we get that the predicted wage is negative. Okay, now this doesn't, if we look at our data, I looked at this data and the value of education is never 0 in our sample. So this is pretty useless for us. What might be useful is this coefficient or the slope coefficient beta 1 hat, right? Which is capturing the effect of education on wages. So this is basically saying as the change in education equals 1, or in other words, the change in education is equal to 1, a change in x is equal to 1, or as there is one more or additional year of schooling, that is going to have an estimated, if there is some estimated effect on y, which is wages, right? And that estimate is equal to $1.43. Okay, so as people get more educated, right, as they obtain one more year of education, their wages are predicted to change by $1.43. Okay, so this is obviously a very old sample of data from 1991. So that's the interpretation here, because we were measuring wages in dollars per hour, and education was the highest degree completed. Now, remember that these estimates, right, because this is from a sample, and this sample may or may not be sometimes representative of what is going on in the population. These may or may not be, these values that we estimated may or may not be close to the population values. And if we obtain another sample of 759, this was a sample of men, so if we obtained another 759 people, these estimates could change. Okay, so this is not so set in stone, right? If you have different sample of data, you might get different estimates. And also sometimes just trying to do predictions of what is y hat based on certain levels of education that don't make sense in your data would give you some strange predictions. Okay, so if we were trying to plug in education equals 0, that was a silly prediction because it gives us a negative intercept. It says that wages are negative. Wages should be strictly positive, right? And so we're trying to extrapolate outside the range of the data, right? So there were no men in this data with education level of less than 8 years. Okay, so it's good to always check the range of your data for X at least when making predictions. Now, if education was equal to 8, then we can plug in 8 for X, right, for education, and then estimate what is the predicted wage, right? So here the predicted hourly wage at 8 years of education is $6.32, right? And in our data, there is probably one worker that earns $6.25. So this is closer to that. Okay, so you're always going to capture some sort of an average effect. Remember that. Okay, so some people will earn more, some people will earn less. We're basically saying on average, the predicted wage for 8 years of education is $6.32 per hour. Okay, let's take another example here, which is looking at this data. You can also play around with this data, vote one data from the Woolrich package. This is looking at what are the effects of campaign spending on voting outcomes. Okay, and so the data is basically for a two-party vote, right, congressional elections. And vote A, the variable vote A, is capturing the percentage of votes received by candidate A. Okay, and share A is capturing the percentage share of campaign spending that's going to candidate A. Okay, so going to candidate A, right? So here we're trying to predict Y, which is vote A, right, as a function of the share of those expenditures on candidate A's campaign. So if you want, you can also run this regression. Okay, basically what we get here is a sample regression function, which says that the predicted vote A equals 26.81 plus 0.464 share of A, right? And here we have 173 observations, okay? So we can do some calculations. We can say, well, if share A was 50, right? If candidate A gets 50% of total expenditures, then the predicted vote would be 50.01, okay, or basically 50. If the share of A increases by 10, okay, here remember share of A is basically calculated as the expenditure on candidate A divided by the total expenditure, right? Let's say A and B were two candidates, right? This is how we're capturing the share. So this is a ratio. This is a ratio. And the maximum value would be 1, right? When all the expenditure is on candidate A, right? Versus 0. So it would lie somewhere between 0 and 1, right? The range of this variable. Okay, so we're basically saying if share of A were to go up by 10, right, which means 10 percentage points, right? This is, we're trying to say if share A goes up by 1, by 10, then the predicted increase in vote A would be 4.64 percentage points. Okay, so here we're basically multiplying by 100 to get to the percentage points interpretation, or here. Okay, now you might want to think about the question whether this is a good estimate of the causalist effect of campaign spending, or is it the case that better candidates just tend to spend more when elections are going on? Okay, so with simple correlation analysis, this will not allow us to infer causality, okay, unless we know that there are other factors that we took care of, okay, that could affect voter support, etc.